Recording.
Yes. Well, thank you very much for the invitation. It's here we have fall, beautiful weather at Notre Dame. We are about 90 miles east of Chicago, and from us, New York is about 900 miles. So if you ever decide to drive from Chicago to New York, on a highway, 80, 90, you're going to pass us after 90 miles just to your right. So, and today I'm going to talk about initial boundary value problems for nonlinear Schrödinger equation. Initial boundary value problems, it's a project that started a little bit more than 10 years ago. And today I would like to, this is a new approach, a new way of studying initial boundary value problems. And I hope those that they see this kind of theme for the first time, I hope they understand, they will get something. So for a good part of the talk, I'm gonna try to be very basic, but after that, things will become a little bit more involved. This is work with collaborators. Focus, I started this conversation with Focus many years ago because he had an interesting novel way of solving linear initial boundary value problems. And then Mazzavinos is his student that visited me at Notre Dame. And Jan is my student, which is now in Virginia Tech. And we have made, we used this linear solving, this novel solving of the linear problem of Focus, and we used it to study well-posedness for initial boundary value problems. But since I want to be really very basic, I hope there are some graduate students or even you may be a professor, but if you don't know a topic, you are even worse than being a graduate student. That's you see, that's the problem with having a phone these days. So I'm going to talk about well-posedness, and I'm going to remind us the definition in general terms. So a PDE problem, initial or boundary value problem or anything, it's well-posed if this problem, think of a PDE problem as a model of a physical situation. So the physical situation evolves over time. We're going to talk about evolutionary equations. So this problem should have a solution in a good function space, because we are not able to solve to find a solution, but existence means there is a solution. We can prove that we have a solution in a big function space, maybe as big as Brazil. So, and as good as Brazil. Then this solution is unique in this space, and also stability. We don't have the butterfly. They always weigh stability. They think about the butterfly flapping her wings in Brazil and creating hurricanes in Florida, like unfortunately is happening right now. But it's not due to the flapping of the wings. It's due to complicated phenomena in our atmosphere. So the solution must be stable. Small changes, perturbation of the data, do not lead to big changes in the solution. If one of these conditions, one of these existence, uniqueness, or stability, existence must always have. Typically, uniqueness and stability may fail. Then we say the problem is ill-posed. And as we said, well-posedness is fundamental for problems modeling physical phenomena or socioeconomic situations. And this meeting has gave us many talks that, okay, now we will, our theme here, if I wanted to focus on a word, only one word, is the word of analogy. Initial value problems for the equations we are going to be discussing, like nonlinear Schrödinger equation and Cordova-de Vries equation, those are dispersive equations. The initial value problem has been studied very well since using Fourier analysis. In particular, big problems has been done since the early 90s. So here what we are going to do, using the Foucault's way of solving the initial boundary value problem, we're going to try to establish an analogy of study of the initial boundary value problem with that of the initial value problem that has been well studied. And in the initial value problem, what we have there, what rules there is a Fourier transform. We do everything via Fourier transform, the global object. Okay, we started with a model, the two beautiful models. One is the KdV equation, the other is the cubic NLS. Let's start with the cubic NLS. And for the cubic NLS, we describe the 3 steps for solving now the IVP. The way it has been done, keep in mind, if you're familiar, in the early 90s using Bourgain spaces. So what we do, the problem, we are going to talk about the NLS, but here is for any dispersive equation. First, we find the solution formula for the linear problem. We replace the forcing, instead of nonlinearity, we use forcing, and then becomes a linear problem. And we want to find the solution formula. We use this solution formula to find linear estimates in good spaces. And then using the linear estimates and the iteration map defined via the solution formula to show that we have a contraction and to establish a solution of the nonlinear problem by proving appropriate multilinear estimates. Let's implement this for the NLS. For the NLS, again, we state the 3 steps briefly. Find the solution of the linear problem, linear estimates, and then contraction via trilinear estimates here. So this is the cubic NLS, this is the cubic nonlinearity, and this is the Schrödinger equation, and here this is the data, okay? And then the NLS evolves the data, and we want to see the evolution UXT, what space it belongs, and everything else. Okay. Now, if we replace the nonlinearity U square U with the F, the forcing, we get this linear problem. And teaching undergraduate ODE, PD, next semester I will be teaching engineers. I will be teaching 300 level course to juniors and seniors. We start with ODEs, but we do separation of variables. And so we can solve this problem here. This is a problem. We take a Fourier transform, which I remind to all of us, if you have never seen it, this is a Fourier transform that has the beautiful property, converts differentiation. This differentiation here will be converted to multiplication by IXC squared here. And then we get a time ODE problem like the one we teach in basic calculus. And C now is a parameter. And if you solve, we get the solution formula. It's just elementary. It's basic calculus. We get the elementary. We are going to turn this procedure for the initial boundary value problem. It will be what we call the novel method of Foucault, solving the initial boundary value corresponding the linear initial boundary value problem. And here I like this notation for data U0 and force in F. We have the solution. The solution S is the solution function. We have this formula. We are going to see this formula for the initial boundary value problem, more complicated. The first line will survive. Then we're going to get more. But that's the way it begins. We have the solution formula. And now, using the solution formula, and getting good spaces. Mathematicians, for some reason, they like Sobolev spaces. The Sobolev spaces that defined through Fourier transform and describes also differentiation and smoothness. So this is the Sobolev space HS, a function that has S Sobolev derivatives, whatever this means. It means precisely this being finite. And then in 93, Bourgain, till then, people were using the Sobolev space, and the solution space was typically, for most problems, Hadamard space. The space of all functions that are continuous in time and Sobolev in spatial variable. Here we have something, a space and the revolution that for linear people like me at that time I was studying, for the linear people, defining spaces that reflect the personality of the linear equation you are studying, that was not. It goes back in the French, call it the French Revolution, in Hormander, Trev, Pfefferman, Stein, Beals, everything, when they were doing pseudo-differential operators in the early, in the 70s and in the 80s, and by, so spaces like that were. But here, for the nonlinear equations, Bourgain defined this. So here in the space, in the spatial variable, we have the typical Sobolev weight, but now we have here another weight here and another parameter B, and this is the symbol of the linear Schrödinger equation. Tau plus xi squared is the symbol. Okay, and now if you try to find, this is the space, and you find the SB norm of the solution formula that we saw before, that's what you're going to do. Let me go to show you this solution formula. You go this solution formula and you estimate it in SB space. And then you're going to be able to bound it beautifully with the norm of the Sobolev norm of the data, but the Bourgain norm of the F is not in the same Bourgain space. This is B, the B parameter here, this B, but B minus 1. You leave the space. And then, in order to have contraction, you have to close the argument, and here what linear estimates comes. And here, this is not difficult. It's just real analysis exercise, nothing exotic. Using the formula and estimating, using Fourier transform and the norms, you're going to be able to prove this estimate. Again, keep this B minus 1. This estimate for the initial boundary value prominence will be minus B here, will be different. And also here, if B is bigger than 1/2, then we get, when we do macrolocal estimates, we get integrability in many places. In the initial boundary value problem, B is not bigger than 1/2, is smaller than 1/2. And this is the estimate for the solution localized. Well, now that you have the solution formula and you have the linear estimate, this is the iteration map, the one you see it in the box. Here was the F, the U0, and the force in F. Now is the nonlinearity here. Now we don't have a solution here, just to have an iteration map. You throw in U, and outside you get phi U. And then you can iterate. You can start with an initial guess and iterate repeatedly, and you hope that this iteration process converges somewhere. And this is how we are able to establish this using these trilinear estimates in Bourgain spaces. It is in the book of Bourgain, has been proved by many people, this. And so what you see here, the B minus 1, this is, here we put the nonlinearity, but since we want to have freedom, we don't put U bar U. We could put U bar instead of G bar, U. We make it more general. This is, you can see that as not a PD inequality. a harmonic analysis inequality, a real analysis inequality, like more or less like algebra property here. So you have, if you have three functions in the space X is B, and S greater or equal to 0, this is the spectacular. You go all the way to 0. And for the periodic problem, Bourdieu established it for the first time in 93. And that was a big revolution. And he got his Fields Medal for this and for more other things, beautiful things. So this is the iteration map that will do what we want to do to get the solution. By the way, this is a technical thing. I want to open a parenthesis for which I'm not going to emphasize in this talk. In our papers, we explain this, but not. That iteration map here, it works, but if you do it, you're going to have for small size data. If you want to deal with large size data, then you have to introduce a cutoff sign. If you have large size data, then you expect the lifespan capital T to be small, and this is the technique, well-known technique, and then using the multiplier estimate of tau, that's the only extra thing. You define the iteration map differently by having localization also inside next to the nonlinearity and using the multiplier estimate of tau. And now I want you to forget this for most of the time, but doing for small data or for large data and doing the most basic contraction fixed point argument, contraction mapping theorem, in Bourdieu spaces, you get if S greater or equal to 0, you have existence and uniqueness. You have a solution, existence, uniqueness. In the Sobolev space XSB, the S parameter S has to be greater than 0, and the B bigger than 1/2, appropriate. It's close, bigger than 1/2, but close to 1/2 depends on S. And the dependence is not just continuous, it's better than continuous. It's not what Handelman likes, it's better than what Handelman likes. And now we are going to move the analogy now. We are going to replace the Fourier transform method to solve the linear problem with the Foucault's method. And again, using the Foucault's method to find the solution formula. We use the solution formula to find linear estimates, more complicated. The formula more complicated, the linear estimates more complicated. And then the multilinear estimates will be a little bit more delicate because the parameter B, the Bourdieu parameter B, is smaller than 1/2, and you have some converging integral issues, but you can do it. We can do it. So this is the analogy. It's the same steps, but we have now a little bit more delicate situations. And now this is, we turn here, instead of having the cubic NLS, we just publish a paper. You will see it later. Out of curiosity, we wanted also to look all the cubic nonlinearities. No bar here. This is the classical integrable nonlinearity of the cubic NLS, 2 bars, 3 bars. For this, we will show the method. So this is the nonlinear problem. And now we don't have just initial data here, the initial data to evolve, but we also have boundary data. This is wherever is boundary in a PDE problem, then interesting things happen. And then we solve it. I'm not going to show the method. Is not complicated. You can, in most papers we write, we provide an outline. You can look at one of our papers and you will see it. But here is the linear problem. We don't have only the initial condition. We also have the boundary condition. The boundary condition here, who makes things interesting, if it was the initial value problem, the solution will end more or less first in the first line. This is where the solution will end. We will have the solution here. And so the first line is like the initial value problem. But because of the boundary, now we don't have, because of the boundary, we have this extra term, which happening here on the boundary of this quarter of the plane, the D plus. Okay, this term here involves only the boundary value, the boundary data, and you have here, because in order to deform, this is the trick, deforming from the line into this plane, then we're going to get this extra term, which is it's a kind, follows from the first line through some symmetry. What is now the transform of U0, of the datum U0 on the half line? This is the half line. It is the half line Fourier transform. And the half line Fourier transform, while it's not a global object, it's good. Actually, it makes sense not only for Xi real, but we can go in the lower plane. For imaginary Xi now is complex, is in the half plane. And then this F is, we take half line Fourier transform for the forcing, and then we take transform with respect to time, and the boundary data transform here, the tilde, is a temporal transform. If we are at time t, we get a temporal transform from 0 to little t. So this is the formula, which is more complicated, and next step is we are going to derive linear estimates. Deriving linear estimates is really very tricky and very delicate. It's not an exercise for a graduate student. This cost us a lot of time to start the project. So what do you have here now? What do you expect? This is the solution. Again, I like the notation. You see now the solution, solution depends, is capital S of initial data, boundary data, forcing. Now, estimate the solution of the initial data, boundary data, and forcing in, this is restriction of Bourgain spaces on R plus time interval 0t. This Bourgain, you will see it later, you can imagine what it is. It is again bounded from the Sobolev norm of the initial data. The natural norm, this is the time regularity, reflects the time regularity, the 2s plus 1 over 4. Having S, time regularity proved long time ago by Koenig, Ponce-Wenger, and company. The boundary data belong here. These two, and then you have the different Bourgain norm, not B, and not B minus 1. Here is minus B. What I told you earlier, here is different. And another big difference here, the B is not above 1/2, the B is below 1/2. So this is the estimate. If you're interested, this is just has been published in JMAA 2024, nicely written paper. If you're interested in it, you will see the details. So now that we have the linear estimates, we are going to define the iteration map through this Foucault's solution formula, and we're going to use this indicates what trilinear estimates we need to solve. This is, again, I will not talk about, but I want to show you what happens for high smoothness. This is for rough data, S smaller than 1/2. In the initial value problem, we didn't have rough and smooth, it was for all S. But here, for this situation and the other situation are different. When you have smooth data, then smooth means here is bigger than 1/2. Then what we have here, we have compatibility conditions, and there are K compatibility conditions. K depends on S, and this is a technicality. Ignore it to see extra complications when you have not technicalities. And here also, because of if you have smooth data, you will encounter also another technical space, is the temporal Bourgain space. The temporal Bourgain space, instead of having the Xi, one-time derivative is two spatial derivatives. So here you have Xi square. Now here you have 2S, you will have S. Okay, So this comes from one-time derivative is equal to two spatial derivatives in the linear Schrödinger equation. I get some red lines. I don't know who puts them there. Okay. Okay.
Now it's perfect again.
Anyone wants has any question? Roberto.
Okay, you can ask.
If anything doesn't go well, let me know. Okay.
Okay.
I don't want to be lonely here.
Oh,
Okay.
one moment. There is somebody, I think, open the.
Anyway, for me,
you can
here,
go.
everything is good. Whatever you see, I don't know, I don't see, but I see something here. I don't know if you see it, but no problem. So this is another technical Bourgain space that arises for smooth data. But we go, and here, the linear estimates. Now, we have two kinds of linear estimates. We have one that the spatial linear estimates, like the initial value problem. Here, the Bourgain norm, restricted Bourgain norm of the solutions is bounded by the norm of HS norm of the initial data, the 2s plus 1 over 4 norm of the boundary data. This, which is similar, this is what we get in initial value. No, here we get similar minus b here, not b minus 1, we get minus b, and we get this extra guy, the temporal, okay? And then we have another temporal estimate for high smoothness data. We are gonna use here only 27, not the 28. These are, okay. And here, of course, for s bigger than 1/2, we need also to skip some values, some integer values when 2s minus 1 over 4 is an integer. Okay, and here again, I remind you what was the classical Bourgain space associated to the Schrödinger equation. This is a symbol of Schrödinger equation. Here is the Fourier transform into spatial and time variable. And this is the restriction of this space, and this is the restriction norm. These are standard functional analytic definitions. And this is, again, we don't have something different space, but simply here we are working on the restriction of Bourgain space, and the b is smaller than 1/2. Okay, now the iteration map is as before. And since we are working on we don't care about small and large data. Here we do the Sybil situation. Instead of F here, we put the nonlinearity. It could be one with no bars, one bar, which is the cubic NLS, 2 bars, 3 bars, any of these 4 nonlinearities. And here the F that in sign has the nonlinearity is this. So this is the iteration map. Now, the iteration map now, instead of F, you see when you got the linear estimate, we have the linear estimate, we have this norm. So instead of F here, we're going to have the nonlinearity. So we have to estimate this norm, and this is what this trilinear estimate is doing. You have FGH here, any nonlinearity, and you will have the these trilinear estimates where the b's are here the way they are below 1/2 but close to 1/2, and the critical indices. The only all of them, if you have no bars, S0 is no bars, S1 is the cubic NLS, the classical cubic NLS, 1 bar or 2 bars, then the critical Sobolev exponent is 0. But if you have all bars there, then it's kind of elliptic. You can go even down. You can go to minus 1/3. So this is an interesting thing. We've got a minus 1/3 for all the other nonlinearities locally look like the cubic NLS, but only the one that has 3 bars goes down. Okay? So this is the theorem. And this trilinear estimate It was proved also for S strictly bigger than 0. We prove it also for S equal to 0 by Erdogan and Girakis. And here now is the main result. It's big, but you don't have to follow the details. We are for rough data, below 1/2. S is bigger than the critical Sobolev exponent, which is different for the different nonlinearity. And the data is in U0 is Sobolev S of the half line. And here the time regularity and everything. With this data, you can find a solution in the restriction space XSB, restriction in this. And you have a solution, so have existence of solution in this space here. And also, the size of the solution is bounded by the size of the data, the way you see here. And we have also an estimate for the lifespan T0. Okay, and these are very technical bits. In this paper that I told you in JMA 2024, you can see all of them. Now, for higher S bigger than 1/2, this is our first paper on NLS. This new method was applied in 2017 transactions. Before that, we have the KDV in nonlinearity, and we use here Hadamard spaces for S bigger than 1/2. Okay, this for the cubic nonlinearities, this theorem was proved by Holmer in 2005 using initial value problem techniques, reducing the linear problem to some initial boundary value problem, linear initial boundary value problem to linear initial value problems. Bona and collaborators using Fourier Laplace transform in time, and Erdogan and Girakis by following a variation of Bona and company. Now, let me also provide the description of the other approaches. I told you this is our approach. Our approach, we use the Foucault's method in order to find a solution formula for the linear IBVP, and then we go like the IVP. Here, Holmer, that they express the linear IBVP as a superposition of initial value problems. And then the Erdogan, Girakis, and Bona, that the Bona company, they do the Laplace transform. And this is not for, this is for KDV, for NLS, for many, many equations. This approach, this is what I'm talking to you today, the new method, which we want to call it analogous to IVP. Now I'm gonna, this is the simpler part now will become more technical just to demonstrate like for this third approach, the Foucault's method approach is much more general and easier to apply. Here now I'm gonna give you an NLS equation with higher dispersion. Instead of putting here having the Schrödinger equation, we put 2, 4, 6, 8, etc. And then here we have quadratic nonlinearities. The nonlinearities here are possible quadratic nonlinearities. The UU, the UU bar, and all bar. And you have many boundary values. You have J boundary values, you know? If J is equal to 1, you have 1. If J is equal to 2, you have fourth order here, then you have 2 boundary values. This is a more complicated problem, but the Foucault's method, it's like the analog of using the Fourier transform that I will be using next semester to solve linear equations. So if you do it and you are patient and you are following the recipe, you're going to find, but you're going to find a much more complicated formula. It's not going to be difficult. All you need to be careful in your computations, and you're going to find more complicated domains. Here are the domains. Here, I'm not going to here if you want. This is, you can go and you can study this later. Here, you're going to have now the Bourgain space. You don't have Xi square here. You have Xi to the M. You have Xi to the M, and you will have compatibility conditions too. And the definitions are analogous. and here are the linear estimates. Now you get linear estimates in the Bourgain spaces again, where again the symbol now is not the linear Schrödinger, is the Schrödinger with higher quality dispersion. So you have that, and then using this linear estimate and the iteration map that comes from the complicated formula, this will help you to define the iteration map. And using this linear estimate, and by linear estimate, you are able to prove this theorem. And here, let me go here. Here we have the critical indices. By the way, you see in all situations, as this dispersion grows, as j goes to infinity, the critical index goes to minus infinity. So this is a very interesting, and this is optimal actually. And this is the theorem. And I want to tell you, we have such a theorem. I finished with the NLS. The second technical part I went fast. I'm very sorry about that. But we have done also an analog like this, a higher dispersion KDV. The higher dispersion KDV is like the higher dispersion NLS. You see it here. And for this, again, we did it long time ago, 2009, with some of my students. We started this curiosity problem. And now we did it also for the initial boundary value problem. This is a JDE 2022 paper. And you see here, the critical index minus j plus 1, 4 goes to infinity, to minus infinity as j goes to infinity. And for m equal to 3, if you set here m equal to 3, you get the KDV result for the initial boundary value problem. The critical index is the same as for the initial value problem. And for m equal to 5, you get Kawahara equation. KDV is integrable, Kawahara is not, but you get, if there are many, many papers on Kawahara, you get the minus 7/4. I have seen some using some other approaches for the Kawahara equation. It's very difficult to do the computation. Here, you can do not Kawahara, you can go as use any dispersion you like. So this is in the KDV direction. Now I'm going to tell you also have done. I'm not describing there are papers here. Each slide is a paper. The Maida-Bielo system. Here we have two KDV systems, identical, coupled. This is for UV here. The first equation is like KDV. The second equation has an alpha, the parameter alpha, the Maida-Bielo. And here, the Wolposeness is very, very interesting. The Wolposeness index here depends on alpha, this parameter alpha. And you see here, if alpha is between 0 and 4, is 0 except in the magical situation where alpha is 1, which is KDV, where you get 3/4, minus 3/4, I'm sorry. You get minus 3/4 at alpha is equal at KDV, for KDV, and when you go above 4. At 4, you get something interesting. You go even above. Imagine, here you go minus 3/4, and at 4 you go to 3/4. So this is a paper, and here is another paper. We have an MKDV system here, an MKDV system. Here we have alpha, and we have a similar. We have a theorem that is suggested by the MKDV Wolposeness. MKDV Wolposeness index is 1/4. This system, no matter what is alpha, the critical index 1/4 does not depend on alpha. And here is the theorem. And by the way, this equation, you will find it, the integral people like Ablovitz and Foucault, etc. You will find systems like that. When they look for integrable system in integrability theory, this system is not integrable, like the Maida-Bielo system is not integrable. But you see this method and deals with integrable and non-integrable objects. And the other interesting thing I sent, Maida-Bielo critical exponent depends on alpha, while this does not depend on alpha. And conclusion, we have done some good progress. We have done NLS equations. We have done KdV NLS equations. We have done KdV equations. We have done systems, and we have done Dirichlet, Norman, and Robin problems. There are lots of problems can be done if anyone is interested. I think some of our papers are written, I think, are readable in the method in general. And obrigado, thanks, and some references. There are many references. Many people have done beautiful work, and one is Brazilian, in fact, Cavalcanti, that has done. I don't know if I mentioned it. Let's see, did we see that, or skipped it to went fast? This one, I think. Yes, this was for the quadratic NLS. For m equal to 2 was done by Cavalcanti in 2017, and the initial value problem was done by Kenning, Ponce, Vega. And here there are lots of people who live it. Thank you.
Perfect, Professor Alex. Very good. Thank you, Professor. Let's open for questions or comments. If everyone have some questions or comments, we have a minute for one question. The audio is open. Everyone can pass some questions or comments for Professor. Alex, in fact, I have a curiosity because
Yes.
if you look your systems, KdV systems, like is a system coupled in the nonlinear terms, right? Look, the Machiavello, you have
Yes.
if you look for just for linear, it's 2 KdV independent. My question is, if you have, for example, the linear couple, for example, for like KdV, but in couple in the linear, in the nonlinear part, we can also use the same approach to get some results.
I don't know. All I can tell you, there are many systems, and there are people standing. I'm telling you, people here, they put many more complicated. This, the theory is very delicate. If you change this, if you change even you perturb alpha, and you see different situations. If you put here different coefficients, and it's even then you will have and put even more linearities, whatever you do. Any system, when you change it, it will be a challenging problem. There are lots of works.
Okay.
Okay. There is nothing I can tell you in general. Even if you tell me a small change, I'm not going to be able to guess what is happening.
Okay, perfect. Okay, let's say thank you again, Professor Alex. Very beautiful talk. Thank you very much.
Thank you very much for the invitation.